Today we're going to be talking about your review worksheet and getting ready for that test that's coming up. Make sure that when you're studying for the test that you don't forget to do your definitions. That's part of the grade for the review, so make sure you do those, and there's going to be several of them on the test. So make sure that you not only find the definitions, but you also study for them. Now, as far as what you need to know the periodic and group trends for atomic radius, ionization energy, and electronegativity. And you can write this on the chart that you've got for electronegativity values. Now, on the test, you're going to get another chart like this, and you're not going to be able to use your own chart. So make sure you know that you're focusing on fluorine for these periodic trends. But as you go across the table and up the table, fluorine may be little in size, small atomic radius, but it's large, okay, for everything else. It's got a large ionization energy, and it's got a large electronegativity. So small size, but large ionization energy and electronegativity values. Down here on the other end, then, as you go down the table and you go towards the left, that's where you're going to get your large size, your large atomic radius. Those are your bigger atoms over here, but this is where you're going to get a small value for both ionization energy and for electronegativity. So you need to know that relationship so you can make those determinations when you're looking at the periodic trends. So know those. You're supposed to know the stability of the noble gases. Knowing that noble gases on that far right column, those are our S2P6 elements. Those are ones that have a full outer shell, a full octet of valence electrons, and those are the ones that are going to be very stable, very non-reactive. They have no driving force to react. The characteristics of metals, ionic compounds, and covalent compounds, you did the worksheet characteristics of bonds. Treat that as part of the review. There are going to be several questions off of that ask you about the different characteristics of metals and ionic compounds and covalent compounds, and you have to know, for instance, that metals are good conductors of electricity when they're solids, but ionic compounds are only good conductors of electricity when they are melted or in an aqueous solution. Covalent compounds are never good conductors of electricity. Those are the kind of things that you're going to need to know. So study that worksheet like it was part of your review. Be able to use the electronegativity values to determine the type of bond formed between the following atoms. Yes, you do need to know the scale. The scale, if you just remember the numbers 0.4, 1, and 2, you'll be able to remember where the breakoff points are for the type of covalent bond. From 0 to 0.39 is your nonpolar. From 0.4 to 0.99 is moderately polar covalent. If you go from 1 to 1.99, you've got highly polar covalent, and anything from 2 on up is ionic. They don't form covalent bonds. The electrons are completely ripped away. So go back to notes 9-5 if you don't remember how to do this, and look at how it's done. An example here, we've got lithium and chlorine. Now, I'm not going to be flipping back and forth to this chart, but remember, if we want to look up lithium and chlorine, you'll have this chart available for you. Lithium is 0.98 for its electronegativity value. So, and chlorine is 3.16. So those are the values you're going to need to find for this. So 0.98 and 3.16 for chlorine then. Subtracting that, we got 2.18 when you subtract those, and that tells you, since it's that 2 or greater, that this isn't even going to be a covalent bond at all. It's going to be ionic. Sulfur, if you look at your chart, sulfur is 2.58. Iodine is 2.66. So we end up with a 0.08 difference. That's well below our 0.4. So that ends up being in the nonpolar covalent range. Nitrogen is 3.04. Fluorine is 3.98. That gives us a difference of 0.94, which falls in the moderately polar covalent range. And again, this table is written out on notes 9-5. You do have to know the scale. And finally, the last one, oxygen is 3.44. Phosphorus is 2.19. That gives us a difference of 1.25. And that tells us that it is highly polar covalent. So those are the different types of bonds that we can have, from the nonpolar ranging up to the ionic, which is a total transfer of electrons not being shared at all. Okay, so in the next part, which element in each of the following pairs has the larger atomic radius? Go back to our chart. We're looking at fluorine versus bromine. So on the chart, here's fluorine, here's bromine. We're looking for the larger atomic radius. Large atomic radius means it's going to be the one that's the lowest on the chart. So it looks like bromine is our largest atomic radius. Gallium or bromine. So let's look at the difference between gallium and bromine. Here's gallium and here's bromine. And we're looking for the larger atomic radius, and large atomic radius down here says we're going to the left, so that means that gallium is the largest. So gallium is a larger atomic radius. Now I'm not going to flip back and forth, but which has the smaller ionization energy? Smaller ionization energy is going to end up, in this case, being barium. It's further down the chart. It's away from fluorine. Remember, focus on fluorine. And the closer you get to fluorine, the larger your ionization energy and electronegativity are. The further away you get, the smaller that value is. So if we're looking at calcium versus argon, calcium's going to have a smaller ionization energy again. It's going to be further away from fluorine. And the next one, it asks for lower electronegativity. Lower electronegativity, remember fluorine has small size but high electronegativity. So we're looking for lower electronegativity, so we're looking at the one that's further away from fluorine. If you look at your periodic chart, you'll see that iodine is further away. And if you're looking at the difference between aluminum and chlorine, you'll see that aluminum is further to the left than chlorine, and it's going to be the lower, therefore, in electronegativity. So you've got to know your chart. Go back to the chart. You've got to know these arrows and that focus on fluorine, that everything going up towards that corner of the chart is going to be a small atomic radius but large ionization energy and electronegativity values. So, okay, next we need to complete a chart like this. Phosphorus, the Lewis dot structure, we need to know that phosphorus, first of all, has 5 valence electrons, which means its Lewis dot structure is going to look like this. Barium has 2 valence electrons, so its Lewis dot structure will look like this. And radon has 8 valence electrons, so it's going to have the maximum number of valence electrons, and its structure, Lewis dot structure, will look like this. Remember, when we're trying to decide how many electrons are gained or lost, The rule is 0 or 8. We either want to lose down to 0 or gain up to 8 so that we will end up with a full outer shell of electrons. So for phosphorus, we could either gain 5, we could either, I did the wrong thing for phosphorus. I don't know if hopefully you picked up on that. But phosphorus only has 5 valence electrons, so it should look like this. Phosphorus could gain 3 electrons to get its 8, or it could lose the 5. It's always going to go, remember, with the least number of electrons it has to mess with. So it's going to gain 3 electrons. Barium could gain 6 to get 8 around it, but it's going to be a whole lot easier to lose 2 electrons. And when we're looking at radon, does radon want to lose or gain anything? And the answer is no, it's not going to do anything at all. So as far as charge, radon's going to have 0 for a charge, and since it doesn't form an ion symbol, it's pretty much not applicable. It doesn't form ions. Barium, on the other hand, loses 2 negative charges. If 2 negatives go out of our atom, that's going to leave it more positive. So this becomes a positive 2 for a charge, Ba2+ for its ion symbol. Gaining 3 electrons, we just got 3 negative particles into our neutral atom, which means that we're going to become more negative, a -3, and we end up with P3- for our ion symbol. So there's another set of information that you need to be able to do on this test. As far as labeling these as having metallic ionic or covalent bonding in them, those types of substances, remember, if it's just a single metal, that's pretty obvious it's going to be metallic. For the others, we need to make sure and remember that ionic compounds are a metal plus a nonmetal, and that covalent substances are all nonmetals. So XeF4, if you look on the periodic chart, both of those are nonmetals, which tells us that this is going to be a covalent compound. Potassium, on the other hand, is a metal, while fluorine is a nonmetal. That's going to give us our ionic compound. On the next part, when we're supposed to give the predominant intermolecular attractive force, remember the rules that we're supposed to go by. The first one is to find out if anything is ionic in it. If it's in ionic substance, we're going to X it out because it doesn't have intermolecular attractive forces. It's not a molecule. They're ionic crystal lattice structures. So check to see if it's ionic first. And if we look at all of these up here, all the carbon, hydrogen, nitrogen, phosphorus, chlorine, all of those are nonmetals. So there are no ionic substances there. So they are all going to have intermolecular attractive forces. The second thing we look for is hydrogen bonding. Hydrogen plus FO or N, because that's going to be the strongest if it's present. And sure enough, right here we have a winner. Nitrogen is bonded to hydrogen. That's going to be our hydrogen bonding. For the top one, we've got hydrogen in CH4, but it's not bonded to FO or N, so it does not have hydrogen bonding. So this one is hydrogen bonding. The next thing, remember, that we have to do is to draw any other structures. And our rule is, if it's polar, then it's the dipole-dipole. If it's nonpolar, then it's London dispersion forces. So that's what we're looking for. So drawing CH4, let's draw CH4 real quick. There are 4 valence electrons in carbon, and each hydrogen has 1, so that's another 4. So we've got 8 valence electrons, 4 pairs. Pretty much we can draw it up here off to the side and see that we've used up all 4 of our pairs of electrons. There are no lone pairs. Carbon's happy. It's got its octet. The hydrogens don't want any more. And since there are no lone pairs on the central atom, it's a pure tetrahedral structure. This is going to be nonpolar. If it's nonpolar, remember, it's London dispersion forces. PCl3, if we draw PCl3, phosphorus has 5 valence electrons. Each of the chlorines has 7. That's 21. That's going to give us 26 pairs of 26 valence electrons, which is 13 pairs. And if we draw this, let me see if I can find a spare place to draw it. We'll just kind of draw it right here. We've got phosphorus here. We're going to have 3 chlorines around it. We've used up, oops, not 4, 3. 3 chlorines around it. We've used up 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The 13th one is going to go on phosphorus. So it's going to have a tetrahedral structure, but it's got a lone pair, and that lone pair is going to make it off balance. It's going to have an unbalanced distribution of charge, which means it's going to be polar. And if it's polar, it's dipole-dipole interactions. So dipole-dipole interactions for our PCl3. Okay, the next section asks which one would exhibit only London dispersion forces. Remember, the London dispersion forces have to be nonpolar. So why, I can already answer the why is that it would have to be nonpolar. And if we draw these structures, you can draw all of them. I'm not going to work through all of them, but our nonpolar structure is going to be the BF3. If you draw it, we end up with a structure that's trigonal planar. Boron does not have a full octet, but it doesn't want a full octet. It's from group 3A, and it's trying to give electrons away in the first place. So the rest of them are going to be polar. They're going to have lone pairs, or they're going to have different electron negativities. So that's the one that's going to be the nonpolar one. Now, the ones that are dipole-dipole are going to be the polar ones. And it's asking us to circle all of the ones that apply on this for which ones are polar. When we draw this one's going to be a pure tetrahedral. We've already drawn it up at the top, so it is going to be nonpolar. If we draw this one, it ends up being a pure octahedral. And you can practice drawing this to see it, but I'm not going to draw through all of them. If you need some practice drawing these structures and finding out molecular geometry, you can look at the videos and notes from 9-4 and 9-6, specifically 9-6b. But that's a pure octahedral, so it's going to be nonpolar. Now this one ends up being weird. I am going to show you what this one looks like, because we're going to have 4 pairs of we're going to have 4 fluorines around here. All of them are going to be full, but this is one of our exceptions to the rule, because what happens is we get lone pairs on xenon. And it looks at first glance like this is going to be polar since it has lone pairs on that xenon. But remember, when we look at what the structure actually looks like, this one ends up being square planar. And it's very symmetrical and balanced. And so it ends up being an exception to the rule. And this one is also nonpolar. So far, none of them can exhibit dipole-dipole interactions. So evidently, we're going, okay, it looks like the last one better be it. And if we draw it, we do find out that it has this structure. It ends up being tetrahedral with 2 lone pairs. So what it actually ends up looking like is more something like this. It's bent. It is not symmetrical. It is polar, and therefore it would exhibit dipole-dipole interactions. Now the last one on this page is looking at whether they can exhibit hydrogen bonding. Remember, hydrogen bonding is H plus either F, O, or N. So it looks like the first one can, because it's H plus F. The second one has H, but not F, O, or N. It's bonded to sulfur, so that one cannot. The next one has H in it, but it has H in it, and it's bonded to an O next to it, which does qualify as hydrogen bonding. The next one is just H. Just H doesn't do it. It has to be H bonded to either F, O, or N, so this is not it either. And finally, the last one, part of it is bonded. We have hydrogen bonded to a carbon, so that wouldn't be hydrogen bonding, but this part would be on the other end, hydrogen bonded to nitrogen. So those are our examples of ones that do exhibit hydrogen bonding. Now, as far as having the lowest melting point, when we're looking at melting points, characteristics like that, we are looking whether it's ionic or covalent. Because remember, if we look at that worksheet I told y'all had to know about, and treat like a review, it will tell you that the lowest melting points are going to be the covalent substances. Ionic substances that have those crystal lattice structures, they're very hard to melt. Think about trying to melt salt. It's just very difficult to do. So we're going to look at whether these are ionic or covalent. And aluminum is a metal plus a nonmetal. That one's ionic. This one is sucrose, table sugar, and carbon, hydrogen, and oxygen are all nonmetals, so there's our covalent compound. And we just said covalent compounds have the lowest melting point, so that means this is going to be our answer. As far as being a good conductor of electricity in solution, it has to have charges, and our ionic compounds are good conductors of electricity in solution. So they're also good conductors when they're melted. Covalent compounds do not conduct electricity at all, no matter what state they're in. If they're really, really polar, they might do it a little bit, but they're still not good. So good conductors are going to be ionic. We look at CCl4, both of those are nonmetals. That's a covalent compound. Lithium and fluoride is a metal plus a nonmetal. There's our ionic compound. There's our good conductor in solution if it's dissolved in water. Okay, the next one asks us to rank from 1 to 4. That's 1 the strongest and 4 the weakest force of attraction. Remember, a full-out bond like ionic or covalent bonding is like bonding your head or your arms to your body. That beats the heck out of any intermolecular attractive force. So ionic bonding is going to be the strongest of all of these. The next strongest is going to be the hydrogen bonding. Then comes the dipole-dipole interactions, and finally London dispersion forces between nonpolar substances with that induced dipole thing going on. That's going to be your weakest of the IMFs, the weakest of the forces. Finally, the last thing you're going to need to be able to do, and there's going to be an entire page of these, you're going to get a cheat sheet. It's the page in your notes that has the table at the top where it lists the different electron pair geometries. There's only 5 of those: linear, trigonal, planar, tetrahedral, trigonal bipyramidal, and octahedral. There are only 5 of them. And then below that is a list of all 12 of the structures that includes lone pairs, etc. So let's work through PF4- real quick. Phosphorus has 5 valence electrons. Each of the fluorines has 7, but there are 4 of them, so that's 28. There's a negative charge, and that means we've got 1 extra negative electron floating around. So that tells us that we have 34 valence electrons, and remember, we like to think of them as being in pairs, so 17 pairs. So let's put phosphorus in the middle. We've got phosphorus in the middle. We've got the 4 fluorines around it. And making the fluorines bond to the phosphorus took 4 pairs of electrons. So we've used up 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Outside gets first dibs, and if we have any left over, where do they go? The center, on the phosphorus, and there's 1 left over. Doesn't really matter where you put it, as long as you put it in a blank space. Don't put it around those dashes that are bonding pairs. We want that lone pair in a blank space. So remember, electron geometry is about how many total pairs of electrons, and this is where people screw up. We've got 4 bonding pairs, but we've got 1 lone pair right here. So there's a total of 5 total pairs of electrons, and our 5 electron pair geometry is trigonal bipyramidal. And you'll get to use the chart again to come up with that. Trigonal bipyramidal. But now you'll need to go to the table below that and look and find which one of the structures has 4 bonding pairs of electrons but only 1 lone pair. And if you'll remember, that's our little hopping robot that's hugging us, and in this case missing a tail. And remember, if you tip him over, he will form that seesaw structure. So this is our 4 bonding pairs of electrons and 1 lone pair structure. The fact that there's a lone pair on the central atom and it's unbalanced tells us that this is going to be a polar structure. And as I told you before, we are dropping the discussion of hybridization this year. So please study